Good morning, good afternoon, and good evening for everyone. My name is Eduardo Murakami. I work at the National Telecommunication Agency, Anatel, and I am a Master in Science student at Polytechnic School at USP. Professor Luis Trintinari and Mr. Agostinho Linhares are my advisors, and they guided me in the preparation of this paper with the participation of Mr. Luciano Alexandre. This presentation is about the paper Coexistence between IMT2020 and ESS passive in the 24 GHz band. This paper is basically organized into these sections. Initially, I will contextualize the work with the motivation that led me to the research and my goals. In the coexistence between the IMT2020 and ESS passive section, I deal with interference scenarios and systems involved. In the methodology section, I talk about the simulations using a tool called Shark developed in Python using the Monte Carlo method. In the seconds, I talk about simulation results and the conclusion in future works. The 24.25 to 27.5 GHz frequency band identified for International Mobile Telecommunication IMT in the World Radio Communication Conference 2019, WRC19, has generated concerns in the weather data prediction community as the use of this band for a future 5G system could impact the weather forecast due to unwanted emissions of this new system. WRC19 established that for the long-term protection of the ESS passive in the 23.6 to 24 GHz frequency band, IMT2020, also known as 5G network, operating in the 26 GHz band, shall limit the unwanted emissions to the following total radiated power value: minus 33 dB in any 200 MHz of the ESS passive band for base station by September 1st, 2027. After this date, the limit of minus 39 dB per 200 MHz will be applied. Passive sensors are used in remote sensing of the Earth and atmosphere by Earth exploration and by meteorological satellites in certain frequency bands allocated to ESS passive. The measurements of these passive sensor operations are widely used in meteorology, climatology, and other disciplines for scientific purposes. They are passive because they do not emit radio frequency energy but measures noise variation from radiation of natural elements. In the scenario under study, ESS passive operates in the band 23.6 to 24 GHz adjacent to 5G networks operating in 24.25 to 27.5 GHz. The area under study, in which the aggregate interference from the IMT2020 base stations and user equipment is integrated, is the same area with the satellite spot beam. The most sensitive sensor used by ESS passive in this band is the sensor F3, whose spot beam size is an ellipse of 18 km and 12 km for major and minor axes respectively. It's expected that millimeter wave deployment in the mobile service will be based on hotspots that will cover a fraction of the built area in urban and suburban scenarios. Recommendation 2101 from ITU specifies that IMT modeling in order to run sharing and compatibility studies between IMT and other radio communication services. One of the key elements in millimeter wave IMT2020 system is the Advanced Antenna Systems. AAS is the general term used to describe an antenna system using techniques that aim to improve the performance and spectral efficiency of radio communication transceivers, take advantage of the theory and practice of active phased array antennas that enable beamforming. The single element antenna spacing plays an important role in determining the shape and gain of phased array antennas. Increasing the spacing between the elements of the phased array antennas can increase the maximum gain of the main lobe, but depending on the phi-scan or theta tilt, can generate latent lobe, which is a side lobe that, due to in-phase contributions of several elements of the antenna, have gains compatible with that of the main lobe, thereby dispersing the radiated energy away from the main lobe. These studies took into account ITUR recommendation 2101, in which, in an adjacent frequency band situation with IMT as the interference system, the antenna pattern of for the emission unwanted can be assumed to have an antenna pattern similar to that of a single antenna element. According to document 3GPP TR37840 of the third generation partnership project 3GPP, the horizontal spacing of the antenna elements is typically 0.6 or 0.5, and the vertical spacing of the antenna elements is typically 0.9. For the study, the AES used a planar panel with 64 elements 8x8 for the base stations and 16 elements 4x4 for the user terminals. ITU Recommendation 2017 provides protection criteria for ES passive system in the 23.6 to 24 GHz band. The reference bandwidth is 200 MHz. The maximum interference level is -166 dB/watt, and the percentage of area of time of allowable interference level can be exceeded by 0.01%. The studies were carried out following the Monte Carlo method, in which during each interaction a number of IMT2020 stations are distributed in the study area and the aggregating interference level generated by all the stations in the other system is calculated. These simulations were performed by using a tool called Shark, which is an open source software that implements ITU IMOC2021. The tool was developed in Python and allows sharing and coexistence studies between IMT and other radio communication services using the Monte Carlo method. The assessment of the aggregate interference generated by 5G hotspots is focused on a non-geostationary satellite operating at an 828 km altitude, and that 355 hotspots are spread over a 169 square kilometer area. The considered network topology is a cluster with 19 macrocells with 3 sectors per cell, with hotspots spread over this area. User equipments are distributed within the hotspot coverage area, and the distance between a base station and the user equipment is modeled by a relief distribution. The azimuth of user equipment in relation to the base station follows a normal distribution. The maximum effective isotropic radiated power of the antenna is calculated using this formula. So the calculated EIRP is 48 dBm for base station and 36 dBm for the user equipment, with power control enabled. The base station carrier is set at 24.35 GHz with a bandwidth of 200 MHz. The range for 23.85 GHz to 24.25 GHz is considered as an out-of-band domain, while below 23.85 GHz is considered as spurious domain. The unwanted emission out-of-band plus spurious limits are defined using baseline reference values of -20 dB/watt per 200 MHz or -13 dBm per MHz for spurious. The unwanted emission defined for out-of-band is -44.5 dBc with measurement bandwidth of 1 MHz. The aggregate interference of unwanted emission from IMT base stations in the direction of ESS station is given by this formula. When the interference value exceeds the protection criterion mentioned above, the difference represents how much should be added in the unwanted emission limits, represented here as a baseline to avoid harmful interference. These figures present the horizontal and vertical radiation pattern of the base station IMT2020 antennas, respectively, comparing different antenna spacings. The curves in blue shows the radiation pattern for an antenna with equal horizontal and vertical spacing of 0.5, while the curves in red present a radiation pattern for horizontal spacing of 0.5 and vertical spacing of 0.9. Both diagrams are aimed for an elevation angle theta equal 105 degrees, that means 15 degrees from birth side, and an azimuth angle of phi equals 0 degree, that means an elevation of 0 degree pointing directly to the sky. As it can be seen, this scenario presents an example of the formation of a grating lobe in a direction that has a significant impact in generating interference with the ESS sensors. This figure presents the aggregated unwanted emission interference generated by the 5G base stations towards the passive F3 ESS sensors, considering vertical spacing of 0.9 and horizontal spacing of 0.7. It's shown only the base station curves once they present higher interference levels compared with user equipment curves. As can be seen in this figure, if it's considered that the unwanted emission domain still presents uniform characteristic of spacing of 0.5, then the results are less critical than the single elements, represented here as a baseline at minus 166 dBm per 200 MHz. However, for element spacing higher than 0.5, the interference is bigger for percentiles around 99%. This study presented baseline simulation that supported WRC-19 decisions regarding unwanted emission limits to protect ESS passive in the 23.62-24 GHz. It also showed one sensitivity analysis with AES element spacing of 0.5 that also was taken into account by the conference. The original contribution of this study was a new sensitivity analysis with different AES element spacing based on 3GPP documents, showing that interference may increase for such scenarios, partially due to grating lobes events that occur for high beamforming theta tilt. As future work, it can be studied limiting the beamforming theta tilt and or include sine lobe suppression techniques as a way to mitigate interference in space service. Thank you very much for your attention.